Hey folks, Doug Blake with Body Design University. Welcome to another weekly study. A real quick recap this week on muscle spindle fibers. I saw a post here just recently, and I thought it would just be a good idea to kind of go over in chapter 5. Now, look, I know chapter 5 for most folks, because it's got all the anatomy and some science and stuff, can be a little overwhelming. But things like the muscle spindle fiber, the Golgi tendon organ are pretty important concepts to understand. These are simply what are known as mechanoreceptors, mechanical receptors. They simply pick up information from the environment, whatever you're doing to your muscles. It picks up that information, and they transfer that environmental information to your spinal cord. Again, it depends on the mechanoreceptor we're talking about. And then tells the muscles to do something, right? So normally, and again, I'm on chapter 5, page 122. And just to clear up any confusion there might be with this particular mechanoreceptor, the muscle spindle fiber, generally over the years, because all of the drawings that are made of muscle spindle fibers, Golgi tendon organs, generally look exactly like what you see in figure 5.6. And if you got your book, 7th edition, open it up, have a look. Figure 5.6. Here's what often confuses people when they look at this picture. And I know initially it's what confused me, many years ago when I used to look at these drawings or illustrations, is the illustration of the spinal cord. And it's the one thing that I want to make sure you don't get confused of it. And it can throw you off, believe it or not. It's not the muscle. You can see in this diagram, you got a picture of the bicep, and they kind of open it up a little bit so you can peek inside to look at what we call the muscle spindle fiber. A couple of real quick terms. Muscle spindle fibers are really just a muscle fiber, specialized muscle fiber, by the way. They are basically non-contractile muscle fibers. We call them intrafusal. It's a good term to know. Extrafusal are those muscle fibers located in the muscle that actually do the heavy lifting. Intrafusal fibers are simply muscle fibers that they go along for the ride as the muscle lengthens and shortens. They get lengthened and they get shortened, but they have a nerve axon wrapped around them. Okay. And I was going to go old school with you here and just kind of draw what it looks like, just so you get the idea of what a muscle spindle is. Again, these are what are known as intrafusal fibers. And I'm just drawing a line to show you that the intrafusal fiber is just a muscle fiber. It has contractile components to it, but it doesn't do any real heavy lifting when it comes to exerting stress to overcome loads. But then it has this nerve that wraps around it. It's kind of like I'm drawing that for you. So I just wanted you kind of see what it looks. It's kind of wrapped around. If you imagine, imagine this marker, and I wrap coil around it, and that's what the muscle spindle fiber is. It's a muscle cell, intrafusal muscle cell nerve complex. So as the bicep, for instance, let me show you that picture again. I hope that's a good picture. Just kind of gives you an idea. It's basically just the muscle cell, and it's wrapped around by the axon of this nerve cell. And so the idea is that as the intrafusal muscle fiber lengthens and shortens, because you're lengthening it and shortening it voluntarily, like you're doing dumbbell curls. So as my extrafusal, or the actual contractile fibers in my muscle, lengthen and shorten through voluntary control, right? I'm flexing and squeezing and lengthening and shortening my bicep because I'm doing dumbbell curls. Those extrafusal fibers, where you have the actin and myosin filaments and the sarcomere, they're doing the heavy lifting. They're overcoming the load that you have placed on them. These intrafusal fibers with the nerve axon wrapped around it, those guys are going for the ride. They're basically lengthening, they're getting pulled and shortened because of the extrafusal fibers. And so when those guys get lengthened and shortened, the nerve that is wrapped around that intrafusal fiber is constantly firing off action potentials, constantly. Okay. Right now, you're sitting there watching this video. I'm sitting here talking to you. If I have electrical stimulus to my muscles, then I have my muscle spindles are always semi-active. They're always under a certain amount of neurological control. So they're always under a little bit of electrical activity, and we call that, believe it or not, it's called tonus, right? And that's what keeps your muscles kind of firm even when they're not doing anything. That's caused by the muscle spindle fibers because they keep a constant level of tension, very slight level of tension through the intrafusal fibers on the entire muscle. And that's important because you need to be able to contract your muscles fairly quickly. So you got this intrafusal fiber wrapped around by the nerve itself, not the nerve body, of course, but the axon of the cell. And so because it lengthens and shortens, just like other fibers do, the nerve itself that's wrapped around the intrafusal fiber, that gets distorted and goes back to place. Think of like a spring. You know, a spring, it's circular, right? And it gets pulled and shortened like this. Well, every time it gets deformed or distorted out of shape, it increases or decreases the amount of number of action potentials per second that it's firing. Now, of course, that's well enough and easy enough to understand as you basically deform this intrafusal fiber nerve complex, increase in action potentials, decrease in action potentials based on the length and the speed at which the muscle is lengthening. That's great. That's easy to understand. The question, of course, is, well, where are those action potentials going? And that is where this other part of the picture comes in. And if you look at figure 5-6, you'll know that there is a blue sensory nerve that's leaving the muscle spindle, right? It goes in and it connects into the spinal column. Now it says spinal cord here, so we'll use spinal cord, but that's just a cross section. And so that picture, this is what always confused me. I was always looking at this going, what the heck is that? It looks like a butterfly. Well, that's just a cross section of the entire spinal cord. They're just looking at a cross section of it, and that's a little sliver, and that's what they're showing you. So the action potentials are either, the action potential frequency is either increasing or decreasing based on whether the intrafusal fiber is lengthening or shortening, right? Because you're doing a dumbbell curl and you're lifting and lowering. And so those impulses, that stimulus, if it increases, is going to get picked up by the spinal column. So you're literally, things that are happening inside your muscular system are being picked up and interpreted by your spinal column. Now remember, mechanoreceptors like the muscle spindle Golgi tendon, they do not send impulses from the spinal column up to your cerebral cortex. So you're out of the picture from here up. You don't have to think about this stuff. The way I normally explain to students is that muscle spindle fibers protect you from yourself, because you would do dumb things as a human. You'd be running and jumping, lifting super heavy weights, dropping things, and you could injure yourself. Well, your body protects you from yourself, right? From up here, your thinking capacity, and keeps everything controlled within the involuntary spinal cord itself. And so muscle spindle fibers pick up this information about the muscle. Is it lengthening? How fast is it lengthening? And basically the muscle spindles send these impulses constantly to your spinal cord. And if you're lengthening the muscle really fast, like if you're letting your arm drop down, well, you can pull the muscle, you can injure it. What the muscle spindles do is they basically say, whoa, dude, you're going way too fast and you're going to hurt us. So we're going to take you out of the equation, and we are going to protect that muscle by sending an impulse back through what's known as a motor neuron, right? That's the red line right there. And it's going to tell the extrafusal fibers, right? The real muscle fibers, right? The real guys that do the actual lifting, and it tells them to contract. You don't have to think about it. This is not a voluntary reaction. This is an involuntary, thank goodness. It's an involuntary movement designed to protect the muscle structure that the muscle spindle is located in. Left to your own devices, you would hurt yourself. It's too much to think about. All the muscles in your body that have to be controlled from a lengthening or speed of length of change perspective. So that's what muscle spindle fibers do. They are designed to ensure that if the muscle is lengthening too far, right? If I stretch my bicep out too far, I can injure the muscle. Look, more than likely, most of the muscles in your body, you're not going to be able to stretch them too far, but there are muscles in your body that if you were to stretch them too far, those muscle spindle fibers, they kick right in and they go, whoa, stop. And they do that involuntarily. Impulses go to the spinal cord then sends an impulse back to the muscle, but this time the extrafusal fibers, and says, guys, contract. Now we see the muscle spindle fiber, or what's known as and this is what the stretch reflex is all about. If you've ever been to a doctor, you know, I don't know about today, but they used to use the little hammers and they'd have you sit down and they'd hit you in the knee. Remember the knee jerk reflex, and you'd like kick your foot out. You didn't even realize it, but doctor would come in with a little hammer and he'd go boop, and your foot would kick out. Well, what was he doing, or she? What were they doing? What they did is by hitting the patella tendon, the insertion down into the tibia, what they were doing was, with that hammer blow, they were very quickly, within a tenth of a second, they were lengthening the quadricep muscle. Yes, believe it or not. So when you hit the patella tendon, it quickly stretches, by the way, very, very small stretch, the quadricep itself, right? And so the quad, because it lengthens real quickly, that very minor impulse from the muscle spindle fibers in the quadricep muscles tells it to contract. What is the doctor testing with the knee jerk reflex? He's not trying to get you upset, and he's not trying to hurt you. He's checking to make sure that your spinal column, that the nerves that go from the knee, from the quadriceps and the lower body, go correctly to the spinal cord, go back, and that's what he or she is checking for, the health of your neuromuscular complex in that area. That's all they do. Last time I went to the doctor, he just like hit it with his hand, whoop, and my foot pops up. It lets you know that everything's from a neurological perspective working fine. So muscle spindle fibers, in short, involuntary mechanoreceptors, muscle spindle fibers, Golgi tendon organs, they tell the muscle spindle fibers tell the muscle, right, involuntarily, you got nothing to do with this, involuntarily, to tell the muscle to contract. This is utilized, go back to my video that I did last week when we talked about the stretch shortening cycle and plyometric training. This is exactly why we do plyometric training, or can do plyometric training, to increase the actual power output of a muscle, because we can now manipulate the stretch reflex to help assist with an increased concentric contraction of the muscle by simply doing a jump on the ground, or something that is what we would call plyometric training. And that not only enhances the stretch reflex, or it gets the stretch reflex to activate, but it also obviously helps from a stretch shortening perspective. And again, if you look at my video from last week, you can go back. I speak directly to actually the muscle spindle fibers. But this week, I wanted to give you a little bit more in-depth understanding of the muscle spindle fiber. Just keep in mind, the muscle spindle fiber is made, it's a complex. It's a muscle fiber nerve complex. Okay, it's the best way to describe it. Those muscle fibers that the nerve wraps around are not contractile fibers, they just go along for the ride. When the big boys are doing their work, right? The type 1, type 2A, type 2X fibers, when they're contracting, the intrafusal fibers, which are basically located deep inside the muscle, they go along for the ride. So as they stretch, lengthen, and shorten, they increase action potential frequency, right? And that information goes to the spinal cord. Now, look, if I'm just lengthening, if I'm just doing this, the frequency of actual motor frequency, right, of those action potentials, I meant to say action potentials, the frequency is going to go up and it's going to go down, but it will hit a threshold level. And when it hits that threshold level where I stretch too far, or I lengthen the muscle too quickly, there's a threshold at which the action potential frequency, once it kicks over to that threshold, bam, the spinal column sends an impulse and says, stop, contract the muscle. And that's why, just as a for instance, just so you know, if like you're stretching out your pecs, you ever notice when you stretch your pecs out or you stretch your quads, you lengthen it and it gets to a certain length and then the muscle kind of tightens up on you. You ever notice that? That's the muscle spindle fibers saying, whoa, 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 what are you doing? Stop stretching me so much. That's what the muscle spindle fibers are doing. That's their basic job inside the muscle. Protective mechanisms, they're your mechanoreceptors. By the way, Golgi tendon organs, just to kind of finish it up, they basically do the opposite of the muscle spindle fibers. Very interesting how they work together, for instance, in reciprocal inhibition, things like this. But if you understand the muscle fiber and you understand that the Golgi tendon organ does the opposite, Golgi tendon organs tell the muscles to relax, right? But they function off of total load. So the amount of tension. So remember, muscle spindle fibers, length, speed of lengthening, muscle spindle fibers, length, speed of lengthening. Golgi tendon organs, load, right? And speed at which the load is added or taken off. Muscle spindle fibers tells the muscle to contract. Golgi tendon organs tells the muscle to relax, because if I put too much load on the muscle, right, too much weight, I can tear the tendon, I can rupture structures, soft tissue structures inside that particular area. Okay, muscle spindle fibers located inside, deep within the muscle belly. Golgi tendon organs, hence the name, located in the musculotendinous area. And so hope that helps. Look, remember, we are focused on helping y'all just get through this NASM exam, pass it on the first attempt. If you've already taken it once and you failed, okay, well, the second or whatever, you are in good company. Okay, we just want to help you to pass it on the first attempt. But if not, look, don't give up, because you'll see in the Facebook group, just as a for instance, lots of folks will chime in and they'll tell you, don't give up. No, as soon as if you do it the first time and you don't pass, you look at the domains that you did not do well in, and there's usually one or two that were low percentage wise. Those are the ones you focus on, and then get into taking that exam within the next 2 to 3 weeks, so that you don't lose the information of the stuff that you did learn. So again, if you have any questions, put them in the comment section below, and just let us know how else we can assist you. Remember to subscribe to our YouTube channel and hit the bell. This way, you know when all of the new information and videos are coming out. As always, it's a pleasure. Have a great weekend, and we will see you next week. Thanks.